or reconfigure using your iPhone wirelessly or over a Bluetooth connection, or a PLC that you can access over the web, and it's just got no password or no security whatsoever, and you can make changes to ladder logic and the state of the PLC. And all that stuff, if you think about it, is really good from a maintenance and operations point of view, because it makes it easy to operate. You don't have to lug a laptop around from device to device every time you want to program it. You just bring your iPhone or whatever around and do it right from there. But from a security point of view, the trade-off just doesn't make sense. So those are the kind of things, the low-hanging fruit that from our point of view, from a control systems point of view, we can take advantage of now, prevent ourselves a huge headache later, and 5-10 years down the road when we've replaced a lot of these systems, we don't want to run into that same problem again. Wade's going to talk to us a little bit about securing your plant and complying with some of the regulations that are out there.
Okay, how to meet compliance and protect your plant. This is all going to be fairly common sense to you folks, but to control system engineers, it's not so common sense. It's pretty new to us. Okay, so rules and regulations out there. Right now, NERC is a big one. They can impose fines of up to $1 million per day per violation. Some of these plants have hundreds of violations. It's geared largely toward protecting the grid as a whole. We also have NIST, which is the National Institute of Standards. These are all voluntary standards. It covers everything from cell phone use to implementing domains, etc. Finally, you have the NRC, which is the Nuclear Regulatory Commission. This is mandatory for all nuclear plants. Compliance is required to maintain your operating license. And they did just recently release new standards. Up until then, it was all physical security. There are many others. We talk about them in our paper. I'm not going to talk about them today. Okay, so real quickly, policies, lists, and procedures. We've seen a lot of organizations spend upwards of a year trying to determine how to arrange their new policies to meet these standards. Here it is. This is what we recommend. You need at least 3 lists. The first would be a sites list. Things like generating stations, backup control centers, distribution facilities. Then you have systems lists, which are internal to each site. So for a generating facility, you might have coal crushers, burner management, control room, etc. And then internal to each system, you'd have devices such as PLCs, DCSs, recorders, PCs, servers, etc. You don't want things like valves or solenoid valves, or any of those components on there, because you really can't protect those devices effectively at all right now. You will need a set of master drawings, your network diagrams. A lot of organizations right now are just trying to create logical network diagrams to give a general idea of where they think a connection might be going. It's not a good idea from our perspective. You can't protect a plant unless you know where every connection and every port is. Okay, so the first procedure you need is policies. It gives a general overview of what compliance standards you have to meet, sets your roles and responsibilities, and gives a general overview of all the other procedures and whatnot. The last 5 are pretty self-explanatory: information protection, physical security plan, electronic security plan, and the 5th one is a pretty big one, so we do feel that one deserves its own procedure: change control and configuration management. You'll also need design guides. You shouldn't plan on these, you should just develop them as the need arises. But ultimately, the goal of this is to design a set of policies that will be compliant with any standards that come out, even overlapping standards. Okay, so the first step of meeting compliance is to identify all your cyber assets, to classify them. Classifications are used to prioritize the devices. Ideally, they should be based on likeliness of attack, ease of attack, and importance to operation. You need to design a comprehensive, automated, and open-ended system. The only way to do this is to track your classifications in a database, to automate your classifications, and to do it in such a way that any new regulations, you don't have to modify your process very much. Categorization is largely focused on categorizing information as top secret, sensitive, etc. Okay, so electronic security controls, network electronic hardening. This is segmentation. This is protecting your network as a whole. First, you got to define a demilitarized zone. Any device that actually touches the outside world needs to be in the demilitarized zone, even if it's a relay or something very simple. After that, you have the primary electronic security perimeters, which is the entire network as a whole. Secondary electronic security perimeters would be a system or a device grouping, and tertiary ESPs would be something like a DCS cabinet 1. All ESPs need to be protected. All access points need to be protected effectively. Device electronic hardening, this is our definition. It took a long time to come up with. It's a lot of legal jargon. I'll just read it real quick. To ensure that only those ports, programs, and services required for normal and emergency operations are enabled, to ensure all security policies are met, and to add or strengthen security mechanisms to result in a more secure system than initial examination revealed. That's compliance for you. Have fun. Okay, so device electronic hardening generally involves these things. You've probably all heard about them. A lot of these keywords are new to control systems engineers. Anyway, you have to do surface area reduction, configuration, and security settings. You have to install protection software of some sort. You need to do communications hardening, limit the protocol use you use, encryption, authentication, etc. Data hardening, as well as hardware redundancy. Hardware redundancy is actually implemented fairly well right now. That's just the way we've been doing it for many years. You don't want an entire plant to be shut down because one computer crashed. Also, you have to account for maintenance. Okay, plant physical hardening. It's pretty much the same thing. You got to define a demilitarized zone. It's generally the area between the plant and the fence that surrounds the plant. You'll generally have 3 or 4 access points there. One for employees where they get in and out of the plant, another one for coal, another one for things like lime or ammonia. You've got to define a primary PSP, which is generally the building of the plant, and secondary is PSPs or rooms. You also got to protect these using something, preferably 2-factor authentication. Here's another legal definition for you. I'm not going to bore you with it. I'm not going to read it, but this is the kind of stuff you got to deal with in compliance. You've got to define these things because the standards really don't tell you how to do it. Anyway, whatever definition you come up with for these things, you got to do it in a systematic way. Area physical hardening generally involves security devices, locks, keys, cameras, etc. Target hardening is focusing on a specific hardening to deter or delay an attack on a specific area. Materials hardening, like Paul said, there's a lot of dangerous chemicals, ammonia, coal, etc. Damage mitigation is things like installing blast walls. Access point management, we already talked about. Environmental hardening is inherent deterrence, such as lighting or shrubbery or installing roads in a certain way. Security personnel policies, patrols, how often you have to go on patrols, how often you got to store your tapes, and how long you got to keep them. And finally, you got to do something about social engineering mitigation. There's not much you can do about it. You can train on it, which they're kind of doing somewhat effectively right now, and you got to control communications, which is kind of limited. Okay, the last thing you got to do to meet compliance is incident response and as well as security reviews. We're not going to talk about that today, but here's a couple standards to get you started. Okay, so how do you protect your plant? The idea is pretty simple. To truly protect a plant, you've got to if you do it right, it doesn't matter what compliance standards you're required to meet. You'll be fine. Just do it right. Okay, our case study is security flaws and mitigation of a programmable logic controller.
Okay, before we start talking about security flaws and mitigation of PLC, let's talk a little bit about some of the assumptions that were made. First of all controls are associated with the PLC. That means all the safeties, all the interlocks, everything is PLC controlled, all the electronic safety as well. Systems are simplified. We have to carry this thing over here, so we have to make it as small as possible. Only vital I/O is represented on our demonstration. Again, process and the logic knowledge has already been obtained. This means is that if you already hacked it, you have to know what the process is. I mean, just varying some variables really won't do anything. You have to know what the process is, and you have to know how to affect it at the right times. Again, these scenarios are conceivable for a percentage of plants, but you're not going to find this in every plant. But be sure there are as many problems as there are processes out there, potential problems. Talk a little about the hardware. We have a PLC of an undisclosed manufacturer. and model. Basically, PLCs came out at the end of the 1960s, beginning of 1970s. American automotive industry wanted to reduce the massive amounts of relay logic they used for the controlling of their installations, so developed the PLC. The network interface module that we have basically comes in two flavors, standard and web-enabled. The one we have basically takes the proprietary serial communication and converts it to proprietary Ethernet communication. Other devices that we have here in front of us, we have a variable frequency drive. I think so this side right here. And we have underneath the board a three-phase motor with that spins the indicator of the wheel. Some other devices are the lights and the switches. Basically, lights present the outputs on by the PLC, and switches present the inputs. Paul, talk about security flaws.
All right, so the security flaws in this device. The PLC that we have here is something that is really common in the industry right now. We're not going to tell you which one it is, but it's something being used all over the world. We set it up and started playing around with it, and it took us only about 2 or 3 hours to find 3 horribly wrong security flaws with this device. The first one is that the device has a module in there, an internet interface module that lets you communicate between the PLC and a computer or an operator station using Ethernet. The module it comes in 2 flavors. All right, there's a embedded web server on that module that lets you just type in the the IP address of the PLC and access the PLC over the web, essentially. The 2 flavors that the device comes in are a non-write enabled device, so a device that doesn't let you write back to the PLC. You can only read data from it, sort of see what's going on. That's the version that we have. There's the other version, which is a write-enabled device that lets you not only read what's going on in the PLC, but change registers and inputs and outputs so that you can affect the ladder logic and anything that's going on in the device, essentially. Probably a little bit less secure device, you would think. What it turns out is that both devices have the same functionality, apparently. When you go to the web page on the non-write-enabled device, the one that we have, it redirects you to a page that doesn't let you write stuff. If you open up the source code of that page, you can look at it and you can tell it's redirecting me this way. But if I go to this other page, I have access to all of the functionality to write to that device. So that's really dangerous because you have the device out there. Somebody thinks, okay, well, I can't write. Nobody can write to this device except through the proprietary software, so I'm safe. So I don't need to set passwords. I don't need to protect it. I'm fine. But that's not the case. They both have the exact same functionality. You can use that to exploit the system. The second flaw that we found is that by default, this thing is not password protected. And when I say not password protected, I don't mean the default password is admin or admin password. I mean they literally thought that password protection was not a feature that people would want to use by default. So it's just not on there. You can password protect it. So if a security-minded person is setting this thing up, they say, even though you can't write to the device, apparently, I'm going to still put a password in there. The password is enforced by a JavaScript, a short JavaScript, which is run on the client's computer, meaning that anyone with a debugger, JavaScript debugger, so something like Google Chrome comes with it automatically, can go in there, look at the code, see what the variables are, see the password that the host is sending you, and you have the password right there. That's all it takes. But it gets even easier than that, if you can believe it. You can also just skip the password checking completely. All right, the web page works by sending commands back to the PLC to a CGI script. All right, so if you know the URL, you know the command you want to send, all you've got to do is send that command to the URL. It skips the password checking completely, making it completely pointless. It also doesn't do any, all the formatting checking and things like that are done on the web page too. So you have potential to do a buffer overflow or send any kind of garbage you want in there. There's nothing checking that stuff. So that's the third one is the one we're going to use right now. We're going to demonstrate a few common functions of a PLC and show you what happens if I'm over here with a script sending commands that I'm not supposed to be sending to the PLC and what the outcome of that's going to be. That is if the demo gods are in our favor. We have a lot of equipment up here, so there's a lot of things to go wrong.
All right, while Jay's setting that up, I'll tell you about this first demonstration. This is a demonstration of a single component, a VFD, which is a variable frequency drive. Mm-hmm. It controls both the speed and direction